Hello, Calculus 12 students. Mr. Yoon here. I just wanted to make another video because the next few classes we'll be learning how to take derivatives of certain functions, such as exponential functions and logarithmic functions. And I want to take this time to kind of make a video to go over some of the proofs that are kind of needed to take the derivatives of these certain functions. This video is all about going over the proofs of how to take the derivatives of exponential and logarithmic functions, and I won't be going over the proofs in class, but I'll be going over more examples in class. Now, for some of the proofs and examples I'll show in this video, I need to go over one of the original definitions of the chain rule. So when I first introduced the chain rule a long time ago, the definition of the chain rule using just calculus notation was dy by dx is equal to dy times du by dx. So this is basically the notation that we use to kind of describe what's happening with the chain rule. And let me just kind of review an example of this before I get onto my examples in this video here. So if we have a question like y equals to bracket 2x plus 3 all to the power of 3, and if I ask you to find the derivative, most students are pretty good with this. They will simply do this 3 times 2x plus 3 all to the power 2, and then they would apply the chain rule here, and that would just be 2. So this is how a lot of students are taking the derivative when they need to use the chain rule. But I want to do this exact same question by using the notation that's kind of given to you at the start of this video here. And if you want to use this notation in order to do the chain rule, what you need to do is you need to find variables. You need to find an expression for y and u. So you do have a y here and you do have a u there. So you want to find expressions for those y and u variables. So to start off, I'll say let y equal to u to the power of 3 for this very same example here. So this 3 is that 3 right there, and I'm simply letting this expression 2x plus 3 just be the letter u. Then I'll say let u equals to 2x plus 4. Okay, and hopefully you can see that because u is the same thing there, and u is that guy right there. Okay, so if you find an expression for your y and your u variables, all you have to do now is you just need to take the derivative now of this expression right here. So if I take the derivative of y with respect to u, this is going to be 3u squared. And if I take the derivative of this guy, since there's a u here, this would be du, and since there's an x here, I'm taking the derivative with respect to x, and the derivative of this guy is simply going to be just 2. Now, if you go back to your definition of your chain rule here, this part right here, dy by du, I mean that's just this guy. That's just this guy right here. So that's going to be 3u squared, and this part du by dx is this part here. So I just simply put the 2 there. So times by 2, and if I go ahead and simplify this, this is the same thing as 3 times u. This u is going to be 2x plus 4. To the power 2 times 2, and with that you do get the exact same answer if you go ahead and take the derivative here. So that u is just this guy right here. Okay, so I just want to, sorry, this first example is a little bit messy here, but I just want to go over some notation for the chain rule because I do need to use this for some of my next examples. Alright, so let's get on with some of the proofs. If you have the function y equals to e to the f of x, and if I want to find the derivative of this guy, so the derivative of e to the f of x, if you look at your reference sheet will say that this derivative is e to the f of x times f prime of x. Okay, so this is given to you in your reference sheet, and what I want to do in this video here is I want to show you how we can actually get to that conclusion. And in order for me to get to this conclusion, I need to use the definition of the chain rule, and I also need to use another derivative rule, which is the derivative of e to the x. This is something that we did figure out in one of our in-class assignments, but the derivative of e to the x is simply going to be e to the x. So I'm going to show you exactly how we can derive this expression here highlighted in yellow by using this statement right here in yellow, and also by using the chain rule notation here. Okay, so in order to find the derivative of this expression here, what I'm going to do here is I'm going to let y, so I will let y equal to e to the u, and then I will let my variable u equal to f of x. Now my chain rule states that the derivative of dy by dx is going to be dy by du times du by dx. So this is the chain rule right there. So let's go ahead and take the derivative of this expression right here, y equals to e to the u, and since there's a y there, so that means I'm taking the derivative of y with respect to the letter u because I have the letter u there. So dy by du in this case is using this statement right here. I mean, that's going to be e to the u, so that won't change. Now for my next statement here, u equals to f of x, the derivative of u, because there's a u there, with respect to x, because there's an x there, well, the derivative of this expression here is just going to be f prime of x. Okay. So if I take those expressions here, this expression, that expression, if I insert that back into my chain rule definition here, dy by du, that's going to be e to the u times f prime of x. And then ask yourself, what does u equal to? Well, u is f of x, so this is e to the power of f of x times f prime of x. Okay, so if you didn't follow that, this f of x is simply that guy right there. Okay, and before I go on to my next proof here, let me just go over a quick example here. So if you have y equals to e to the 2x, and if I want to find the derivative, this is going to be e to the 2x times just 2. Okay, let's move on to the next proof, or the next example. So another derivative that we'll be talking about in class is we want to take the derivative of an exponential function. So this is going to be just a to the x. So we're moving away from e to the x now and moving with your just general a to the x, where a is a constant. Okay, so if I want to take the derivative of this, basically, the answer would be a to the x times ln a, and this is something that's in your reference sheet. So I just want to take some time and kind of talk about how we get to this conclusion here. So if I have an example here like y equals to 2 to the x, so if I have a function like that, and if I want to find the derivative, then we would have to use this rule right here. So y equals to this example right here, this is just your basic exponential function, so it's increasing, right? So if you want to find the derivative at any given point, we would definitely use this expression right there. Now, in order for me to kind of derive this next proof, there's a few things that you need to know. The first thing you need to know is you need to know the change of base formula. So what that means is if you have something like ln, or so not the change of base, but your if you have a ln expression like ln, for example, 2 to the power 3, and your lns and your natural logs, they do have these rules where if you have an exponent there, you can actually bring that down to the front. So that would be, this would be 3 times ln 2. Okay, so you need to know that rule right there, and this is very similar to the pre-calc 12 stuff, where if you have something like this, I mean, you can bring this exponent down the front. It behaves the same way. So for this next example here, you definitely need to know this statement right here. And another statement that will be useful for this next proof is that the derivative of ln x from one of your in-class assignments, the derivative of that is going to be 1 over x. So you can go back to your in-class assignment and just verify that this derivative is true. And in order for me to kind of complete this proof, I need to use those two statements to kind of help me through here. Okay, so I'm going to delete this now, and let's get on with the proof here. So let's just start off by saying that y equals to a to the x. Okay, now what I'm going to do next here is I'm going to ln each side, so I'm going to multiply each side by ln, and if I multiply each side by ln, I haven't mathematically changed my expression here, so I can do that. So moving forward now, this will be ln y, and if I use this rule here highlighted in yellow here, if I use this rule right here, I can bring this exponent down to the front, so that's going to be x times ln a. Okay, so now that I've done that, what I can do next is, what I can do next here is I can take the derivative now of each side. So if I do that, this is the notation that I'll be using. I'm taking the derivative of ln y equals to the derivative, taking the derivative of the right hand side now of x times ln a. Okay. Alright, so let's go ahead and take the derivative of the left hand side and the right hand side. Now, in order to take the derivative of this expression right here, you're just using statement number 2 there. So this will be 1 divided by y, but then you need to apply the chain rule and you need to take the derivative of y now. So the derivative of y is dy by dx. Now, when you move to the right hand side, if you want to take the derivative of, sorry about that, if you want to take the derivative of this expression right here, you have this x term being multiplied by ln a, and ln a right here, this is just a constant. Okay, so for example, like ln 2, it's just a constant. So hopefully you can recognize here that you need to apply the product rule here, and if you apply the product rule here, you need to take the derivative of the first term. So the derivative of x is 1 times ln a plus the derivative of the second term. Well, the derivative of a constant is going to be 0 times x, which is the original or the first part. And if you go ahead and simplify this, this will be ln a plus 0, and then you have 1 over y times dy by dx. And since we have this dy by dx, let's go ahead and isolate that. So dy by dx is going to equal to y times ln a. Okay. And then ask yourself, what does y equal to? Well, you need to go all the way back to the beginning of the problem, and you'll notice that y equals to a to the x. So if I go ahead and plug this back down into here, I get dy by dx equals to a to the x times ln a. Alright, and that's the proof of the derivative of sorry, that just shows you the proof of this statement right there. And before I go on to my next proof there, let me just go ahead and just do a simple example here. If I have the function y equals to 2 to the x, so remember this 2 right here is a constant, right? So those things are constants, right? So if I want to take the derivative of this, this would be y prime equals to 2 to the x times ln 2. Okay, so there it is. That's the, a derivative of an exponential function right there. Okay, let's move on to the next proof. Alright, so the next example that I want to go over is if we have the derivative, if we're taking the derivative of another exponential function, let's just say I have one second here. Alright, so sorry about that. The next derivative example that I want to show you is if you take the derivative of a constant to the power of any function, that will be, according to your reference sheet, will be the constant to the power of the function times the derivative of your exponent times ln a. Okay, I just want to say that this derivative right here is different from in the previous example. We had the derivative of a to the power of x, and this is going to be completely different from what we have right now. Okay, so in this next example, we're working on these kind of problems where your exponent can be any function, like a to the power of sine x, or a to the power of x squared, or a to the power of 1 over x. Whereas the left hand side, this is always going to be like 2 to the power of x, 3 to the power of x, 6 to the power of x. Your exponent here will always be x. And in my next example, I want to give you examples where the exponent can be any kind of a function. Okay, so this next proof is a little bit different from the previous proof, but in order for me to kind of finish this proof, we do need to use the fact from the previous proof, and that is if I want to take the derivative of any anything to the power of x, like a constant to the power of x from the previous example here, this is going to be a to the x times ln a. Okay, so I do want to use this statement to help me continue on with the proof for this next example here. Okay, so now in order to do this, I have to do, this is basically a continuation of the chain rule again. So if I have my definition of my chain rule here, dy by dx is going to be dy by du times du by dx. I'm going to show this next example by using the chain rule here, and that means I need to find let statements for my y variable and my u variables. Okay, so I'm going to say let y, let's see, let y be, since I'm dealing with this part right here in blue, I'll say that let y be a to the power of u, and then I'll let u be, well, u is just f of x, right? Okay, so I haven't really changed anything yet. I'm just making new definitions for my variables here. So you know, this u right here is that u right there. So I still will have, if I combine these, I still have y equals to a to the f of x, right? Okay, so let's go ahead and now take the derivative of these two let statements here. So if I want to take the derivative of this statement right here, I have a y there to start, so this will be dy by du. And the reason why I have a u here is because there's a u there, and the reason why I have a y here is because there's a y there. So the derivative of y with respect to u is going to be, well, if I go back to, if I want to take this derivative here, I go back to this first statement here, and that's simply going to be a to the u times ln a. Okay, and if I want to take the derivative down here, I mean, this one's not bad. This is going to be du by dx. And once again, the reason why I have a u there is because there's a u at the start, and the reason why I have an x here is because there's an x there. So the derivative of f of x is just f prime of x. Okay. Now let me go ahead and just erase some of these things now, just to clear up some space. Erase that now. So if I go ahead and just insert this into my chain function here, so if I take this part right here and replace that with that, then I will get this. I get a to the u times ln a times du by dx, which is just right down here, which is f prime of x. And if I go ahead and substitute all my values for u, ask yourself, what is u? A to the u, well, here is u, right? U is f of x, so this will be a to the f of x times ln a times f prime of x. Alright, and if you just kind of rearrange the terms here, you get a to the f of x times f prime of x times ln a. And this expression right here does indeed match up with what you have on your reference sheet. Okay, so that's how you derive that derivative. Alright, now before I continue, let me just do a quick little simple example here of this derivative in action. So if I have something like y equals to 5 to the power of x squared, and if I want to take the derivative here, this would be y prime. Alright, so let me just rewrite the derivative of this on the side here, because I know this is still new here. So the derivative, the derivative of a to the power f of x is going to be a to the power of f of x times f prime of x times ln a. Alright, so this is indeed on your reference sheet, but let's just use it now for this particular problem here. So the first part is I need to have a to the power of f of x. Okay, so that just means I just rewrite the original question, and slight little mistake there. Alright, and then I need to have the derivative of the exponent. So what is the derivative of my exponent here? Well, that's going to be 2x. And then the last part states that I need ln a. Okay, so what's ln a? Well, a is just, you know, the base there, so my base here is just 5. Okay, so there it is. There's my derivative of this example right here. Alright, let's move on to the next one. Alright, so the next example that I want to go over, now we're switching from exponential functions into ln functions. So I want to show you that the derivative of ln of any function and this is I'm just going to copy this from your copy this out of your reference sheet here. This is going to be 1 over f of x times f prime of x. Okay, so I want to show you how do we get to this conclusion now. And in order for me to kind of show you how this works, I do need to take another. We need to recall this other derivative here. So if I have the derivative of ln x, according to your in-class assignment, this is going to be 1 divided by x. Okay. Now for this example here, I'm going to continue to derive this by using the definition of the chain rule here. So the chain rule, the definition of the chain rule was dy by dx equals to dy by du times du by dx. And that means you need to find let statements for your y and your u variables. So let's say y equals to, so this is my original function here. I'm going to let y equal to ln u, and that means u has to be f of x. Okay, and right away I'm just going to go ahead and take the derivative here. So dy by du equals to 1 over u. And this statement right here, the du by dx, this is going to be f prime of x. Okay, and after that I go back to my definition of my chain rule here. So where's dy by du? Well, that's just this statement right here. So that's going to be 1 over u, and then I have this du by dx, which is right here. So I replace du by dx by f prime of x. So this will be f prime of x. And then ask yourself, what is u? Well, u is f of x, so this will be, this u right here, if you don't see that, that's this guy right there. So that's going to be 1 over f of x times f prime of x. And that's how we get, so this expression right here does indeed match what you have in your reference sheet there. So that's how you derive the derivative of ln of f of x. And just before I move on to the next proof here, let me just kind of do a quick example here. So if I have ln of, 2x squared plus 1, y equals 2. And if I want to take this derivative, that's going to be 1 over everything on the inside. Sorry, let me get rid of that. That's going to be 1 over everything of the inside term, which is going to be 2x squared plus 1. And then you take the derivative of the inside guy, which is going to be 4x. And if you want to go ahead and simplify that, that's simply going to be 4x over 2x squared plus 1. All right, let's go ahead and move on with the next proof. All right, I just have 2 more proofs to go and then we're finished here. So the second to last proof is if I want to take the derivative of a log function now, log of base a of x, according to your reference sheet here, this will be 1 over x times 1 over ln a, right? And in order for me to show you this proof here, we need to once again rely on other properties here. And one property that you need to know is if I have the log of base a of b, using a change of base formula and using the natural logarithm, this is the same thing as ln b divided by ln a. Okay. And for those pre-calc 12 students, this is the same thing as log of b divided by log of a, which so I'm claiming that these 2 expressions here are equivalent. And if you don't believe me, then all you have to do is just go to your calculator and just say, hey, if I do go to my calculator and do log 2 divided by log 4, and if you do ln 2 divided by ln 4, I guarantee you will get the same numerical example. So this is one identity that we need to use for this proof here. Okay, so that's one identity that I need to use, and the other identity that, or the other property that I need in order to solve this problem is I need to know that the derivative of ln x, alright, so this is once again the derivative that we did in our in-class assignment. This is going to be 1 over x, right? So I need to use these 2 properties to kind of help me construct the proof for this next example here. Okay, so the question is, what's the derivative of this guy right here? So I'm going to start off this problem not by using the chain rule, but by just saying, let's just say y is the function. All right, so there is my original question there, and then I'm going to use property number. I'm going to go ahead and use property number 1 here, and that means y will equal to ln x divided by ln a. Alright, so that's property number 1 in action there. And then what I can do next is I can just rearrange the terms. So this will be 1 over ln a times ln x. Alright, so I haven't really done anything there mathematically. I've just kind of rearranged the terms there. And then what I'm going to do next now is I'm going to go ahead now and take the derivative of this. So I'll just say this is y prime or dy by dx, but y prime is fine. And also this expression right here highlighted in yellow, that's just a constant, right? So for example, like ln a, I mean a, this letter a is just a constant, so this could represent like ln 2 or ln 3. Those are just numbers, and that's going to be important because when I take the derivative of that expression, I know that the derivative of a constant will be 0. Now, this whole expression right here that I'm circling in blue here, if you want to take the derivative of that, I mean, it's the same thing as applying the product rule right here. So let's go ahead and apply the product rule here. So what is the derivative of this expression in blue? Well, that's just a constant, so the derivative of a constant is 0 times the other part, ln x, plus 1 over ln a times, and what is the derivative of ln x? Well, the derivative of ln x using statement number 2 over here is going to be 1 over x. Okay, so if I go ahead and simplify this, y prime is going to equal to 1 over ln a times 1 over x. And that looks very similar to what we have over here in our original proof here. Looks very similar. All I have to do is just kind of flip, move this guy to the front here, so that's 1 over x times ln a. And that is it. I won't do an example of this. I'll do an example of this in class, but there's the proof for that. And then finally we can move on to our last proof. So let's go ahead and continue on here. So the last proof that I want to go over is if I want to take the derivative of log base a of f of x. Alright, so this is slightly different from the previous example because the previous example just had x for this part right here, but I want to take the log of any function. And if I want to take the log of any function here, according to the reference sheet, this is going to be 1 over f of x times f prime of x times 1 over ln a. Okay, so for the next this final example here, we'll go ahead and derive this, and we'll finish off with the final example, and then we'll call it a day. Now, for this final proof here, I need to rely on 2 other properties again. So the first kind of property that I think would be important for this kind of problem would be log of b of a is the same thing as ln b divided by ln a. So very similar to the previous example. And another property that I need to know is if I want to take the derivative of the ln of f of x, this is, we just derived this this derivative right here, so that's going to be 1 divided by f of x times f prime of x. Okay, so using those 2 properties, I should be able to finish this last proof here. Okay, so let's go ahead and start this last proof. So I'm going to start off by saying y equals to log base of a of f of x. All right, then I'm going to go ahead and apply this very first property right here, and I'll do this in green now, or no wait, black still. So y equals to sorry, it's not right. If I apply that property, it should be ln f of x divided by ln a. Okay, and then I'm going to go ahead and rearrange the terms here. This is going to be 1 over ln a times ln f of x. Okay, and once again, for this kind of a question, you need to recognize that this part right here is a constant. All right, so that's important because once I take the derivative, which will be my next step, the derivative of a constant is 0. So when I take the derivative of this dy by dx, I'm essentially using the product rule here, and the derivative of this part highlighted in yellow, as mentioned, it is 0 times ln of f of x plus 1 over ln a times the derivative now of this expression right here, and that's where I need to use this second property right here. So we've already gone ahead and derived that. So that's going to be 1 over f of x times f prime of x. Now if I go ahead and just kind of clean this up here, this is going to be dy by dx. Just rearranging the terms here, I'll put this part in front, so that'll be 1 over f of x times f prime of x, so I'll put that part next. And then I'll put the constant at the very end, which is 1 over ln a, and that's just this part right there. Okay, so there it is. There is the final proof of taking the derivative of a logarithmic of any function there. And before I just kind of finish this up, I do want to go over one problem here. So if I have something like y equals to log base of 3 of maybe sine x, right? So if I want to take that derivative, let's go ahead and apply this rule here. So the first part of the derivative says I need to do 1 over f of x. So what is f of x? Well, f of x is this part right here, so that will be 1 over sine x times, well, now I'm going to times by the derivative of sine x, and the derivative of sine x is cos x, times 1 over ln a. And what is ln a? Well, this a part is, that base there, so it'll be 1 over ln 3. And if I went ahead and simplify this, this would be cos x over sine x times 1 over ln 3. And if you know your trig identities here, cos x over sine x is going to be cot x times 1 over ln 3, which is the same thing as just cot x divided by ln 3. Okay, so this expression right here, this cot x stuff, I mean, that's just a trig identity that you can get from your reference sheet as well. Okay, all right, so there we go. I know this video was a bit long, but it did save me about half an hour of time in class where I don't have to do the proofs. Instead, in class, I'll just go ahead and do the examples. All right, we'll see you guys later.